Lesson: Predictive Analysis for Vulnerability Exploitation. Predictive analysis for vulnerability exploitation is a vital area within cybersecurity, especially as threats become increasingly sophisticated and frequent. The CompTIA CySA Plus certification underlines the importance of understanding and managing vulnerabilities using artificial intelligence to predict potential exploits before they occur. This lesson focuses on elucidating actionable insights, practical tools, frameworks, and step-by-step applications that cybersecurity professionals can leverage to enhance their proficiency in this domain. The cornerstone of predictive analysis in vulnerability exploitation is data. Massive amounts of data from various sources, such as network traffic, system logs, and incident reports, provide the foundation for predictive models. These models use machine learning algorithms to analyze patterns and identify potential vulnerabilities before they are exploited. For example, anomaly detection algorithms can be employed to recognize deviations from normal behavior, which may indicate a potential vulnerability or an impending attack. One practical tool that professionals can use is the MITRE ATT&CK framework. This framework provides a detailed matrix of techniques used by adversaries, which can be mapped to specific vulnerabilities within an organization's infrastructure. By leveraging ATT&CK, cybersecurity teams can prioritize vulnerabilities based on the tactics and techniques most likely to be used against them. This prioritization is crucial because it allows organizations to allocate resources efficiently and address the most critical vulnerabilities first. Incorporating AI into vulnerability management involves several steps. First, data collection and pre-processing are essential. This step includes gathering data from various sources and cleaning it to remove noise and irrelevant information. Next, feature selection is crucial. It involves choosing the most relevant data attributes that will improve the model's predictive power. Tools like scikit-learn in Python offer efficient methods for feature selection, such as recursive feature elimination and feature importance scores. Once the data is prepared, the next step is model selection and training. Machine learning models, such as decision trees, random forests, and neural networks, can be trained on historical data to learn patterns associated with vulnerability exploitation. Decision trees, for example, are particularly useful for their interpretability and can be visualized to understand the decision-making process. Random forests, an ensemble method of decision trees, provide robustness and accuracy by averaging the predictions of multiple trees to reduce overfitting. After training, the model is validated using a separate dataset to evaluate its predictive accuracy. Cross-validation techniques, such as k-fold cross-validation, help ensure that the model generalizes well to new data. This validation step is critical, as a model that performs well on training data but poorly on unseen data is of limited practical use. Metrics like precision, recall, and F1 score are used to assess the balance between false positives and false negatives, which is crucial in a security context where missing a true positive can have severe consequences. Once validated, the model can be deployed in a real-world environment to monitor systems and predict potential vulnerabilities. Continuous monitoring and model updating are necessary to adapt to new threats and changes in the system environment. This dynamic approach ensures that the model remains relevant and effective over time. A case study that highlights the effectiveness of predictive analysis is the use of AI by companies like Microsoft to enhance their vulnerability management processes. Microsoft employs machine learning models to analyze billions of signals from their products and services to identify vulnerabilities proactively. By doing so, they can issue patches and updates before vulnerabilities are widely exploited, significantly reducing the risk of attacks. In addition to predictive models, integrating threat intelligence into vulnerability management enhances the ability to foresee potential exploits. Threat intelligence platforms gather data on threat actors, their tools, and techniques, providing context that can be used to refine predictive models further. By integrating threat intelligence with predictive analysis, organizations can gain a more comprehensive view of the threat landscape and adjust their defenses accordingly. Another practical framework is the NIST cybersecurity framework, which provides guidelines for managing cybersecurity risks. It emphasizes the importance of identifying, protecting, detecting, responding, and recovering from cyber incidents. By aligning predictive analysis efforts with this framework, organizations can ensure a structured and systematic approach to vulnerability management, enhancing their overall security posture. To address real-world challenges, professionals should focus on creating a culture of security within their organizations. This involves training staff to recognize and report potential vulnerabilities and fostering collaboration between IT and security teams. By doing so, organizations can leverage collective expertise and insights, leading to more effective vulnerability management. In conclusion, predictive analysis for vulnerability exploitation is an essential component of modern cybersecurity strategies. By utilizing AI and machine learning, organizations can anticipate potential threats and address vulnerabilities before they are exploited. Practical tools like the MITRE ATT&CK framework and the NIST cybersecurity framework provide valuable guidance for implementing these strategies effectively. By continuously updating and refining predictive models and integrating threat intelligence, organizations can stay ahead of adversaries and protect their critical assets. The integration of these methodologies not only enhances an organization's security posture, but also optimizes resource allocation, ensuring that the most significant threats are addressed promptly and efficiently.